Good morning, good afternoon, everyone. My name is Mady, and it's a pleasure to be here today. This work was conducted in collaboration with Dr. Wael Elsersy. Our presentation is titled From Data to Defense, an analytical overview of how machine learning and deep learning models perform in context of network intrusion detection system, or NIDS. The central question driving this research is simple but critical when it comes to detecting network intrusions. Which model actually work and under what condition? So let's find out. The agenda. We will start with the fundamentals of intrusion detection system, what they are and how they work. From there, we will discuss the benchmark dataset we used and why we choose them. Then we will cover the models we evaluated, both classical machine learning and deep learning approaches. After that, we will dive into the results and the analysis followed by our conclusion and a look at the future direction of this research. Intrusion detection system. So, what exactly is an intrusion detection system? At its core, an IDS monitor network or system events and analyzes them for suspicious activity, automatically alerting administrator. When something looks wrong, there are two main detections paradigms. The first is signature based, which works by matching traffic against a database of known attack patterns. It's highly effective on known threats, but it completely fails against zero-day attacks or anything that hasn't been seen before. The second approach is anomaly-based detection, which uses machine learning or statistical methods to identify deviation from normal behavior. This approach can detect unknown attacks, but it tends to have a higher false positive rate, and it's heavily dependent on model and dataset quality. Also, there is a host-based IDS, a single device, great for deep visibility but limited in network coverage. Also, there is network-based IDS. On the other hand, it monitors network traffic across the entire infrastructure. It provides broad coverage, so it struggles with encrypted traffic. NIDS is the focus of our study for today. The benchmark dataset. For our experiment, we used two well-established benchmark datasets. The first is KDD Cup, a classic in the field generated from 1989 DABRA data. It contains roughly 4 million records, 41 features, and 22 types of attack. The major limitation here is that it's dated. It doesn't reflect modern network traffic well. The second dataset is the New South Wales dataset, released in 2015. It's more modern and realistic dataset with about 2.5 million record, 49 feature, and 9 attack categories, including exploit, fuzzers, and DOS, and others. Its key advantage is that it captures realistic contemporary traffic patterns. One important challenge shared by both dataset and something we specifically addressed in our experiment is significant class imbalance. We applied smooth oversampling to handle this, and we will see how that affected results shortly. Why these datasets? You might ask, why these two specifically? There are four main reasons. First, they offer complementary complexity. KDD Cup provide a well-structured, simpler baseline ideal for benchmarking. New South Wales is harder, with modern traffic and more severe imbalance. Together they span the full difficulty spectrum. Second, they pose community standards in network intrusion detection system research, which mean our results are directly comparable to prior work and reproducible by others in the field. Third, their contrasting characteristics. Different errors, feature counts, and class distribution and attack style. And fourth, both datasets represent class imbalance and pre-processing challenges that many prior surveys have glozed over. We wanted to study these effects directly, especially the impact of smooth, which bring us to our model selection. Proposed models. We evaluated 7 models in total, mix of machine learning and deep learning approach, which are Decision Tree, Random Forest, XGBoost. On the deep learning side, we evaluated 4 neural architectures: ANN, 1D CNN, LSTMs, CNN-LSTMs. The rationale for the selection was to get a comprehensive picture of classical methods known for efficiency versus modern deep learning architecture, known for expressiveness. Results for New South Wales dataset. Now let's look at the result. Starting with the harder dataset, New South Wales at the first glance, almost every model achieved over 95 accuracy. That's look impressive, but here is the key insight. High accuracy is misleading when the data is heavily imbalanced. A model can achieve 95 accuracy simply by predicting the majority class most of the time. That's not useful for intrusion detection. The most informative metrics are balanced accuracy, F1 macro, and G mean, which account for performance across all classes. By this metric, Random Forest was the clear winner, achieving 56 balanced accuracy and 48 G mean. Every other model, including all deep learning model, performed worse. What is striking is that the model CNN-LSTM, despite its complexity, achieved nearly a 0 G mean, meaning it failed to detect minority class attacks on this dataset. The same is true for ANN, LSTM, and CNN. The takeaway here, complexity doesn't equal performance when the data is challenging and imbalanced. The KDD Cup dataset. Here all models performed exceptionally well. Random Forest achieved near perfect score, 99 accuracy, 99 balanced accuracy, and 99 G mean. XGBoost was right behind it. Even deep learning models like CNN-LSTM and LSTM achieved balanced accuracy above 96%. The one notable outlier was that CNN alone achieved 62 balanced accuracy, but with smooth, it jumped to 97% balanced accuracy, which is a great improvement. For inference time, decision tree is the fastest at 0.03 seconds, while CNN-LSTM take up to 3 seconds, which is an implication for real deployment time. The broader lesson for KDD dataset: when the data is clean and well structured, model can perform well. But New South Wales dataset tell us which models are actually robust. So what do we conclude? Random Forest and XGBoost emerged as the best overall performance, strong balanced accuracy, near perfect F1 score on the KDD, and the best trade-off between performance, speed, and memory. In simple methods clearly dominates the study. More broadly, on structured tabular data, classical machine learning consistently outperformed deep learning. Deep learning models showed high raw accuracy but misleading scores due to the class imbalance, and they came with significant computational cost. For real-time deployment, Decision tree came with 0.03 second inference time, which make it the top choice in latency critical environment. CNN-LSTM, on the other hand, came with 3 seconds and requiring more memory. Is simply not suitable for production in IDS. And one critical finding on Smooth, it helped deep learning models in KDD, but actually it hurted all model on high dimensional New South Wales dataset. Our recommendation is to use Random Forest with Smooth on complex high dimensional dataset. Future directions. Looking ahead, there are 5 directions we see as the most promising for this research. First, transformer-based architecture. Unlike LSTM, transformer use self-attention for parallel processing and global pattern capture. Early IDS studies show competitive results with better training efficiency, and they could address the bottleneck we observed with CNN-LSTM. Second, adaptive and online learning. Models that continuously update as attacks, patterns, and network behavior evolve rather than being trained once on a static dataset. Third, we need more strong algorithms for handling data imbalance. Fourth, unified evaluation framework. There is a critical gap in current network intrusion detection research. Inconsistent pre-processing metrics and dataset splits make cross study comparison nearly impossible. Standardization is needed. At fifth, federated and privacy preserving NIDS, training model across distributed network without centralizing sensitive traffic data. That brings us to the end. Thank you for listening.